When an aircraft is flying at any height significantly more than its own wingspan, the development of wingtip vortices is unaffected, and the vortices will have their normal effect of upwash in front of the wing and downwash behind it. However, during takeoff and landing, proximity to the ground, at heights less than the aircraft's wingspan, will prevent full development of the vortices, which reduces the upwash and downwash. This, in turn, causes the effective angle of attack of the wing to increase. This, with the associated aerodynamic changes which occur, is known as ground effect. This lesson examines what happens when an aircraft is in ground effect. Generally, lift will be increased and induced drag will be reduced. In addition, the reduced downwash will affect both longitudinal stability and tailplane pitching moment. The influence of ground effect depends on the distance of the wing above the ground. A large reduction in the induced drag coefficient, CDI, will only occur when the wing is very close to the ground, that is, within about half a wingspan. If we take a few examples from the graph on the screen, which plots reduction in CDI against the ratio of height to wingspan, or h/b, we can see that for an aircraft with a wingspan of 40 meters, or 131 feet, the reduction in CDI is only about 1.5% at a height of 40 meters. That is, with a height-span ratio of 1. As the height comes down to 10 meters, a ratio 0.25, the CDI has dropped by 23.5%. But at 4 meters, a ratio of 0.1, the induced drag coefficient has fallen by a substantial 45%. The height of the wing above the ground when the aircraft is in the landing attitude is determined by its mounting position on the fuselage. From the graph just used, it was seen that the last few meters of descent make a big difference to the reduction of drag coefficient, so it can be said that low-wing aircraft will experience a greater degree of ground effect than high-wing aircraft. Whilst ground effect may possibly change the aerodynamic characteristics of the tailplane in its own right, a low-mounted tailplane will have its effective angle of attack modified by the change in downwash. As the aircraft comes into ground effect, the tailplane loses downforce, causing a nose-down pitching moment. A high-mounted tailplane may be above the influence of the change in downwash angle, and therefore not suffer the same disadvantage. Assuming a tailplane is affected by changes in downwash, it is interesting to consider how the camber of the tailplane will affect the result on its pitching moment. Looking first at a positively cambered tailplane, ground effect creates an increased upforce. In other words, a nose-down moment. If the camber is negative, the change in downwash produces a decrease in the downforce, and again, the result is a nose-down pitching moment. With a symmetrical tailplane, the effect is similar to the negative camber, so it can be said that a decrease in downwash will always result in a nose-down pitching moment. The opposite is true of increased downwash. Ground effect is not the only cause of changes in downwash. Flap movement and the formation of shock waves at transonic speeds will also alter the airflow, so appreciation of these phenomena is an important factor in a full understanding of the principles of flight. Increasing downwash, G to D, gives a decrease in tailplane effective angle of attack, and decreasing downwash, D to G, gives an increase. It is important to understand the effect of changes in downwash on the tailplane's angle of attack, but vital to understand their influence on pitching moments. Let's consider an aircraft entering ground effect, assuming that CL and IAS remain constant. As the aircraft descends into ground effect, the following changes take place. The decreased downwash will give an increase in the effective angle of attack, which requires a smaller wing angle of attack to produce the same lift coefficient. If a constant pitch attitude is held when entering ground effect, the increase in lift will reduce the rate of descent or cause the aircraft to level off, an effect known as floating, which lengthens the landing distance. Additionally, the decrease of induced drag will cause a reduction in deceleration, and any excess speed above the correct threshold speed could lead to a considerable float distance. The reduction in power required might also give the aircraft a tendency to rise above the intended descent path to the runway, known as ballooning, unless power is reduced. If the airspeed is allowed to decay late in the final approach, and the pilot attempts to arrest the ensuing increased sink rate by raising the nose, increasing the angle of attack, the wing may stall on entering ground effect, resulting in a heavy landing. The pilot may need to move the control column aft in order to restore sufficient downforce to achieve the desired landing attitude. The loss of downforce is due to the decreased downwash over the tailplane and the associated change in the effective angle of attack. Changes in the airflow around the aircraft may cause differences in pressure error in the pitot static system. Local pressure at the static port is likely to increase, which will make the airspeed indicator and altimeter under-read. The effects of climbing out of ground effect are generally the opposite to those of entering. If we again consider an aircraft climbing away with a constant CL and IAS, the following changes will occur. The lift coefficient will reduce, requiring an increase in angle of attack to compensate. The drag, and thus power required, will increase. The increase in downwash will generally produce a nose-up pitching moment, so the pilot will have to move the control column forward to compensate. The pressure error change, which would occur on entering ground effect, is reversed, with a small local static pressure decrease and a slight increase in ASI and altimeter indications. It is possible to become airborne in ground effect at an airspeed and angle of attack such that, after leaving ground effect, the aircraft could sink and even settle back onto the runway. It is therefore vital that the correct speeds and attitudes are used for takeoff. The nose-up pitching moment may induce an inadvertent over-rotation and tail strike. This lesson concludes the section on lift, which is a basic part of the principles of flight which requires a thorough understanding, since a good deal of the remainder of the syllabus is concerned with the application and management of the forces involved. The next section deals with drag, a force closely allied with the generation of lift.